The Explainer. Today, we're breaking down the architectural plans for your data. Database Schema Design. It's that invisible framework that honestly makes the difference between an app that's zippy and reliable and one that's just a complete mess. Let's get into it. So, let's start with a bit of a riddle. What does a super messy closet, you know the one with clothes just spilling out everywhere, have in common with a massive multi-million-dollar database that runs a global company? The answer, as it turns out, is, well, everything. Because without a solid plan, both of them just fall into total chaos, right? You can't find anything, and they basically become useless. For a database, that critical plan is called its schema. Think of it as the architect's blueprint that lays out exactly how every single piece of information gets stored, how it connects, and how you get it back out again. So, if you're the architect here, where in the world do you start drawing up these plans? Well, it turns out there are four main schools of thought, or philosophies, for how to even approach the design process. First up is what we call the top down strategy. This is a lot like how an artist might start a painting. They begin with a really broad sketch of the whole scene, right? You start with a super high level, kind of abstract view of your data, maybe just a few big ideas, and then you slowly, piece by piece, refine it, adding more and more specific details as you go. Now, the total opposite of that is the bottom up strategy. And this is like building with Legos. You start with the absolute smallest individual bricks, the specific data points like a first name or a product price, and you start assembling them into bigger and bigger structures until, boom, the entire model takes shape. There's another cool variation called the inside out strategy. With this one, you identify the absolute most critical pieces first. So, for an e commerce site, that's probably going to be your customer and product tables. You get that core relationship perfect, and then you build everything else, like orders and shipping and reviews, outward from that solid center. And of course, in the real world, you don't have to be a purist about it. The mixed strategy is pretty much exactly what it sounds like. You might tackle one part of your database top down while you build another part from the bottom up, and then you just combine the two. It's all about using the right tool for the right part of the job. All right, so once you've got a design philosophy in mind, it's time to get your hands dirty. Let's move on to the actual construction plan and see how this blueprint becomes a real functional database. And you know what? There's a pretty widely accepted six-step process to follow. This six-step plan is really the core of it all. Step one, you have to identify the purpose. What are you even doing? Tracking inventory? Managing user profiles? Step two, you normalize the data. This is a fancy way of saying you organize it to cut down on repeating yourself and to keep it clean. We'll talk more about that in a minute. Three, you pick the right data types. Is something a number or text or a date? Getting this right is so crucial for performance. Four, establish relationships. How does a customer actually connect to an order? Five, you use constraints, which are basically the rules that protect your data from getting messy. And finally, step six, you optimize for performance. You make sure everything runs fast. Now, this is where things get really, really interesting. Because even with the most perfect plan in the world, you are always going to face trade-offs. And probably the most common battle is between creating a perfectly structured, academically pure database and one that's just lightning fast. And this slide just illustrates that battle perfectly. On the left, you've got normalization. It's all about data purity, getting rid of any repeated data. The trade-off? Well, queries can be slower because the database has to jump around to lots of different tables and piece everything together. On the right, denormalization. Deliberately duplicate some data. Why? To speed things up. But you run the risk of your data becoming inconsistent. It's a classic dilemma. And here's another key trade-off: partitioning. Vertical partitioning means you split a table by its columns. So for example, you could keep a user's login info, which you need all the time, separate from their profile bio, which you hardly ever look at. This makes logins faster. Horizontal partitioning, on the other hand, splits a table by its rows. So you might put all your customers from 2023 in one chunk and all the ones from 2024 in another. This makes managing a giant table way easier. Okay, finally, just like any well-built house, a database needs a set of rules that you just can't break. This is what keeps it stable and reliable for years. You can really think of these as the official building codes for your data. In database speak, we call them constraints. And these are some of the most critical building codes you'll ever see. A primary key, for example, gives every single record a unique ID, so you never ever confuse one student with another. A foreign key is like the glue that holds your tables together, making sure that an order record is always tied to a real customer. And when you've got constraints like not null, which sounds simple but are totally vital, they enforce basic rules like making sure every employee record actually has a last name. And this really gets to the heart of the whole thing. Like the quote says, great schema design isn't just some technical exercise. It's about deeply, truly understanding the data itself, its context, and exactly how people are going to use it in the real world. That understanding is what separates a brittle design from a really robust one. Which really just leaves us with a final thought to chew on. Your data is always trying to tell a story. The question is the blueprint you've designed for it strong enough to let that story be told clearly for years and years to come? Or is it a structure